Hi everyone, I'm Adan, responsible for open source at OpenBNB. Since we have newly open sourced a new version of MiniCPM-V, which is MiniCPM-V 2.6, it's a multimodal which has achieved impressive results. I'm here to introduce how to deploy it efficiently. We choose vLLM for deployment. Here, I will mainly introduce two ways to use vLLM. The first method is using Python code to call vLLM for inference. The second method is to first start an HTTP server with vLLM, and then use Python code to call the HTTP server. To perform model inference, first let's introduce the first method using vLLM's Python code for model inference. The first step is to download and install vLLM. The code for this tutorial has already been written. We just need to copy it. Find the directory which we need to download it. This directory can be an empty folder. Copy the code here, then start to download. After waiting for a while, we can see it has completed. Now, in the current directory, which will be a vLLM folder, let's enter this folder. After entering the folder, type pip install and a space and dot, then press enter. This installs vLLM using the code we just downloaded. I have already installed it, and it takes quite some time, so I won't demonstrate the installation process here. After completion, we move on to the second step, which is After completion, we move on to the next step, which is writing the current Python code. The code is already provided in the tutorial, so you can directly copy and paste it. After copying and pasting, the first code modification is in the image section. This line of code is where we input the local path of our image. We need to provide a local image path for inference. Here, I'm using this airplane image. The second part is the model name. We have two options. First, write the local path of the downloaded model. It must be an absolute path. Here, I have MiniCPM 2.6 downloaded. Copy the path and paste it here. This is the first method. Writing the absolute path of the local model. The second method is to input Hugging Face ID of our MiniCPM-V. The difference between these two methods is if we input the local path, we call the local model. If we input Hugging Face ID, it will download model from Hugging Face, then performs inference. So that is the difference. Next, let's take a look. There's a parameter here to note. Max model length refers to the maximum input length of the model. Here it sets to 2048. This is because I'm using 4090 GPU. If your GPU is better, you can increase this length. It refers to the maximum input length. If your GPU isn't very good and it lacks memory, you decrease this number. Next, let's take a look at the message. In the content field, there will be an image placeholder. There are two special image symbols. We don't need to worry about them. The picture. This refers to our input image, which means that kind of questions we need to ask about this image. This part can be modified. After making these changes, the rest of the code generally doesn't need to be altered. Here note that there is a parameter for sampling, which is our decoding parameter or generation parameter. I actually don't recommend making too many modifications to this parameter. You can adjust this. Maximum output depth. If you are performing a high-resolution OCR task, you might want to increase this because you might need to output a lot of tasks. You can set it to a higher value, for example, 248. Next is the model generation, which is the model inference. Note that there are two methods here. The first is single-threaded, which means providing one image and task at a time. Other method is multi-threaded, which means vLLM handles multi-task and images simultaneously, handling multiple tasks and images currently. Let's look at the differences. In this case, the dictionary rewrite contains two fields. One is prompt, the other is multi, which is a multimodal field. The field actually specified image, which is the encoding of our image. This is for single-threaded processing. Now, load the model and start the prefilling operation. After prefilling, it will proceed to decoding, which means generation or decoding. Generation has started, entering decoding. The output is two segments of task, but actually we see only 0. I printed out, meaning there's only one result, split into two segments. Since we use single-threaded processing, the output is also single-threaded. Now let's try multi-threaded processing. To use multi-threaded processing, comment out this line and uncomment the line below. The line below is actually a list, which each element is a dictionary. The format of this dictionary is the same as for single-threaded processing. That is, when using multi-threaded processing, just combine multiple dictionaries in the list and perform the generation. Organize the data in the same format into a list and proceed it with the generation. Now the model loading process starts again. And then let's move to the prefilling stage. We can see that it shows 2 because there are 2 elements in the list. With 2 elements, decoding happens simultaneously. So the currency level is 2. We can see that it directly output 2 elements. There's a 0, there's a 1, right? The generated results are almost identical because the input were the same, 2 identical inputs. This is explain how to use vLLM for both single-threaded and multi-threaded processing. Next, I will explain another method. For the second method, we still need to install vLLM. Since we already installed it, we can skip this step. Next step is to start the vLLM service. Here, let me explain these parameters. First, the command is vLLM. We don't need to explain this. It's the command name. It means starting a service, starting a HTTP service. The following part specifies the model's address. You can also use the name from Hugging Face. It will then download the model. Model written after the type field actually indicates the precision of our model, which we'll use for calculations. Auto means is automatically assigned it. In this case, it should be used the precision of FP6. The one here is the maximum length, which we've already discussed. For our model's maximum length, we can set it to 2048. Next is quite important one called API key, which can be understood as the password for our service. Since you've started this service, you don't want everyone to be able to call it. So this is the password you set when you start this service. What follows here is a code for trusting the remote. And actually, we just need to add the parameter to it. Okay, that's inputted. Alright, now it's loading the model. We can see that the model service has started, which means the model is now on standby on our HTTP. What we need to do next is to wake up this service or to call the service. Let's take a look at this code next. This code has actually already been provided to us. Let's look at a few parameters that we need to pay attention to. First, there's one called OpenAI API key, which is actually our password. We've already set a password, so we just fill in the password we set earlier here, and then next is our HTTP address, which is the default when we don't need to modify it. Then we are creating this service, which is initialing the service client, which can be sort of as a client. For the client, we input our address and this password. And then the most important part is what we are going to do next, which is to make the service call. The call is in this format. Let me explain some of the fields in this format. First is the model name. If you wrote a local path for your model earlier, you just copy the local path here. If you wrote the one here earlier, if you wrote the Hugging Face ID, then we just write the Hugging Face ID here. I just wrote the local model path earlier, so it's still the local path here. Next is the message. This message is the parameter we're going to pass to this HTTP server this time. For this parameter, it should include a few things. First is our text, right? So we write it in the text. Note that when we enable the HTTP service call, we don't need to use this specific symbol for images to occupy the place in front. At this point, we write an online image address. We write the address in the field at back. Copy this into the field, and we'll first use the request to get this image, and then send this image and text together to our model. Finally, some quite important is that we need to input an end token, which means that when the model generates up to a certain or several tokens, it will end. This is our end token, and will end when it generates these two tokens. Hold on, it should be calculating. We can see the output here. Let's first take a look at the image, okay? This is the image, and let's see its description. More importantly, I want to explain to you the structure of the output. Let's take a look at the output structure. I've down to output there. The first output is the direct output of the client reply. This output, we can see, has a certain structure body, right? It has structures, so we can see that there were actually many fields here, which fields we extract. This is the choice field inside. The response actually contains a lot of fields, so this is distinguished for everyone. That's all for today's instruction, so happy coding for everyone. Hi everyone, I'm Adan, responsible for the open source project at OpenBnB. Since we have newly open sourced a new multimodal named MiniCPM-V 2.6, which has achieved excellent result. So today I will explain how to use llama.cpp to perform inference with MiniCPM-V 2.6 model. The first thing we need to do is to get the llama.cpp branch of OpenBnB. It will be merged to the official repository in a few days, but at least we need to copy the branch of our GitHub. And first we copy this line of code. After copying this line of code, we find the place where we want to download it. That is where you want to download llama.cpp. Then we put it here. Enter the command in the desired path with using bash. Of course, since I have already downloaded here, so I won't demonstrate this part again. I already have the same code. That is this code. Let's try. Of course, since llama.cpp already exists here, it won't be downloaded again. Once we have downloaded it, after downloaded, we need to input a make command. Of course, already compiled it here, so the speed is relatively fast. If you're downloading and making it for the first time, it might take some time. So be patient. That's all we will discuss for this part. Alright, let's continue. After the compilation is successful, the next thing we need to do is to get the code of GGUF. For the GGUF format code, there are two options available. The first option is to get the GGUF weight. We go directly to our official GitHub. We have already converted to the MiniCPM-V 2.6 model into the llama.cpp format, which is the llama.cpp format. You can go to the address and download it directly. You can choose either the Q4KM or FP16 file. You only need to choose one of them. Q4 is actually a quantized version of the model. The other is non-quantized. The latter is FP16, which has a higher precision, but it might be slower to take up more weight. And next, I will introduce another method, that is, if we don't want to download the model converted by OpenBnB, what should we do? We need to download this branch and the model in the code. After downloading the model, I will show you we get this file. This file is actually our MiniCPM stored file in a safe tension format. Okay, we just need to run this line of code. You want to place the model weight and download it here. Just enter this. Of course, you will need to access Hugging Face. After enter this line of code and waiting for it to download, we will get the file, which is our current MiniCPM-V 2.6. Of course, your format name might be different from mine since I have changed it. File name explained. Alright, after getting this, what we need to do next is to start converting. Let's take a look at this line of code. Copy it and paste it into your llama.cpp directory. We already made llama.cpp. Let's run this line of code in llama.cpp path. But here we need to pay attention to one more thing. There's something that needs to be modified here. That is after -m. it actually needs to select our current model. This model is the one we just downloaded. The pass of the PyTorch model. For example, this one. This is the model we just downloaded. So we copied it over, and after copying it, we run it. It will take a long time, so I will pause it. I will show you the result once it's done. The address we enter is the model's path. What it actually does here is to break down our multimodal. It separated language model and the vision model, so we can see after this line of code is executed. Let's take a look after the line of code. In the previous PyTorch model path, several new things have been added. One is the new model folder. In the model folder, we can see that it contains many model weights. These model weights are actually the weights of the language model. They are quite large. Additionally, we can see there's a file named MiniCPM-V and another MiniCPM-V project. These two files are essentially our model. So next we need to convert the language model and the vision model into the GGUF format separately. And let's take a look at our tutorial where this is actually included. Next, this line of code converts our vision model, converts our vision model. Let's take a look. Alright, we should see this line of code here. Pay attention to this. There are several parameters. After the first -m, we input the language model. Actually, it's our PyTorch model, this path. In this folder, the path of the folder can be written as relative path. Next, this MiniCPM-V project is actually so what we input here should be the address of the project module we obtained earlier. So here we should write MiniCPM-V 2.6. You need to write the path of the MiniCPM-V project. Let's run it. This should be relatively fast. Okay, it's running now and will finish in a short time. Once it's done, we will get a path and we can see this path. This is a newly generated GGUF file for the language model. Next, we also have a vision model. We also need to convert it to the GGUF format. Next is this line of code. This line of code is to convert the vision model. The path still needs to be placed in llama.cpp, locating the previous mentioned model file. This is the address of PyTorch file model we downloaded from GitHub. Then we need to save it to the specific directory. This is the content in the model folder generated earlier. We need to save it to the location. This contains the model folder we generated earlier. replace the path address to the model folder. The start may take some time, so I will pause temporarily. Since I already performed the conversation earlier, the relevant file already here. This is the generated language module file. So after obtaining these two modules, we can proceed to an optional step. The step is whether to quantize the module. Quantization is usually done in the language model because its weight proportion in the model is relatively small. Copy the address of the language model into the address that need to be quantized. Then save the quantized model to the specific directory. Copy the address of the address at the front is for the quantized model, and the address at the back is for saving the model. Save the model to the model folder. Run the quantization process. Beware of the file permission. They were incorrect earlier and then made adjustment. The quantization has already started. The quantization result is in int4 format. Some use int6. Let's wait for a moment. It might take a while, so I will pause again. Next, let's take a look. Before quantization, it has an F16 suffix. We've now quantized it to K4, which means being quantized to int4. This will actually have lower precision compared to previous F16. Roughly a quarter of the original precision, though slightly more than a quarter. Okay, after quantizing the model, let me explain something else. For Macs, I recommend using the int4 model because it uses less memory. If you have a better GPU and need higher precision, you might need F16 model. For the edge devices, I still recommend the int4 version, that is the quantized version. Next, we will start inference. Let's begin. This is the image inference. MiniCPM-V 2.6 supports image inference. We do inference and the multi-image inference. Let's take a look at how image inference is done. Let's run it here. It may take some time. Let me explain the parameters here. First, the entry function is this compiled one. The file name llama.cpp MiniCPM-V clip. Then the -m parameter specify the address of the quantized language model file in int4 format, and the project, which is essentially a multimodal project module for the projection module, is specifying the address of the quantized non-quantized image module, GIF format. The -c specifies the maximum length of the model, and the tempo is the temperature parameter in deep setting. Top P and top K are also the parameters, and this is the coefficient for repetition penalty. If you want it to generate less repetition, you can increase this parameter, but generally it's best to leave it unchanged. The last parameter is -m, which you can specify the address of the image you need. When we see that it's generating, we ask it to perform OCR, let's check the accuracy. Initially give an overview of the in-commerce and then the conversation method and etc. Then you discuss narrow a-commerce and they provide a good description. The communication method listed here are most correct. Okay, let's see the generation speed is quite fast. This is our okay. Next, let's check the video recognition or its video capacity. Okay, we inputted here. Since processing may take a bit longer, we'll pause and check the result. After a while, it generated a result. Let's check what the video actually shows, what the video display. First is the operating system and the application and browser, etc. Let's take a look at the video and check the video. The video initially shows an operating system, including organization toolbars and tabs and etc. will be shown everything. You can compare the video yourself. Additionally, the FAQ will be released along with the document. This document will include many updates and additional information on issues that may arise, aiming to provide a better user experience. Okay, that's all for today's instruction. Happy coding. Don't forget to give us your following, your star, and goodbye. See you next time. Hi, our developer friend in front of the screen. I'm Adam, responsible for the open source at MiniCPM-V. We have just open sourced the MiniCPM-V 2.6, which is a multimodal that has achieved very excellent result. So in this channel, I will show you how to perform inference using Ollama. It's worth mentioning that we have submitted our code to Ollama. In a few days, we'll get a merge, which means that we can directly download the model from the official Ollama. So you won't need to perform those operations, making the process simpler. So okay, first let's introduce how to create how our code work. The first step is following the previous llama.cpp method to obtain our quantized model. Mainly in this, I will show you the model, which is a dual GPT model. Here I'm using a dual GPT model for demonstration. Okay, the second thing we need to do is we get our OpenBNB branch of Ollama. Let's take a look. The code is already copied in this tutorial. We will copy the coding from the tutorial, then find the address we need to use, which is the downloaded address for Git. Of course, I have already downloaded here, so after you download it, you will get the Ollama code from GitHub. Once we have the Ollama code, we enter the main path of the Ollama code, then go to the LLM directory. So next we need to do is to git clone the llama.cpp code from OpenBNB. Here is the code. We copied it. Inside the LLM folder, we just enter this line of code. After entering this code, it will download. Once the download is completed, we will get the llama.cpp code, which we have modified. This code is on OpenBNB, but it will soon be merged to the official llama.cpp repository. Okay, after completing these two steps and downloading the two codes, we need to return to the Ollama directory, which is under this. We open it and note that we need the environment to be CMake to 3.24 or above. Go version should be 1.25 22 or above in GCC 11.4 or above. So for Mac users, I have provided command to install these 3 environments, but I just copy and paste them. I have already executed them, so I won't run them again. We see that it will copy quickly. It's updating now. Once updated, the environment will be registered, and as we had just entered it, it won't compile again. This is the go generate. We need to go to the Ollama directory and then enter this line of code. Since Ollama is written in Go, we enter this and will quickly running, but I will interrupt it as already stored and compiled it, so I won't do it again. The next step is to boot, to compile. We are still in the Ollama directory and enter Go. After entering, it may take some time. Let's see, a little more than half a minute, but it's quite fast. So here I have already compiled, so I won't execute again. I will interrupt it. Next, you will get an executable file. After a successful compilation, what we need to do next is to input this command. What does this command do? It starts an Ollama service. Let's start the Ollama service here. Note that what we discussed earlier is that what you need to do for the first time when we successfully compiled Ollama. For now on, each time you start Ollama, you just need to navigate to the Ollama directory and input this command to start Ollama. Next, I see what need to do is to create the model file, which is actually a configuration file for Ollama. Let's input this. After inputting, what we need to do here is input the following lines of code, or rather, these configuration options into the modify file. Note that we need to modify certain parameters. The fastest parameter is the address of GGUF format language model that you created earlier. The second is the FP 16 GPU model generated with llama.cpp. Specify the address of the tool model in the two positions. Without much modification, it will work. Let me pause here to find the path. Once you find the address, you just need to input them. We save and exit using WQ to read them into the file. After writing, you will have this MiniCPM-V 2.6 model locally. After we have created the modified, we need to create an Ollama instance. To create the Ollama instance, use the command Ollama create MiniCPM. Okay, of course you can name it whatever you like. Here then because it's a multimodal version, after the instance is created, we can check it out. This might take a time. Here Ollama V 2.6 model is created. Was created 7 seconds ago. Just now, to run this model, we use the command Ollama run. Enter the model name, copy the model name we just earlier inputted. After running, it will prompt for input. Here we input our information. This is our prompt. Let's check the recognition. Here's the prompt separated by a space. Then input our file. This will take some time. I will pause for a minute. Alright, it's generating because of the length limit. It might not generate everything. We set a maximum length while creating modifier rate. The accuracy should be decent. Let's see the summary of electronic business communication, etc. Let's stop here. The conclusion of today's instruction. I want to remind you of a few things. First, if you encounter any issues, refer to the FAQ in our tutorial. It addresses many problems encountered during installation or compilation. Check if your issue matches any listed here. Secondly, the official Ollama team will support our code. Keep an eye on our GitHub for simpler, more user-friendly updates. That's all for today's instruction. Happy coding. Don't forget to give us your star and follow us.